Okay, year 12. So let's start off with a wee retrieval roulette today. So answer these in your blue book and then I'll give you the answers. So here's the answers. 6 and 10 were both diagrams. If you just look those up in your Knowledge Organiser self-quizzing booklet for me to mark those. Okay, let's start on to today's work then. So last day I had asked you to do the questions on page 224 and 225. It was a wee mishmash of questions on direct current, alternating current, and then on Fleming's left-hand rule. Now, before I put my answers down here, please don't judge how horrendous, how bad my diagram of the wee hand is. Also, some of you are in no position to judge. Alex, yours was quite funny. Dylan, hilarious. It looked like a shark or something. Nathan, I don't know what was going on with that diagram. But also, some of you really put me to shame. So, Abby and who was it? Abigail, both of yours were very impressive. Yeah, you really put me to shame. Jake conveniently missed that part out of his picture. And let me think, there was another couple that I thought, oh, that was a good idea. Oh, Sam drew, you drew the like a diagram showing it, that like not the hand, so the coil in the magnetic field. Very clever. You avoided trying to draw the hand. And Shane, you described it again. Very clever. So good work. Now, yeah, please don't judge. Promise. So this is on page 224. We had to use a diagram to state Fleming's left-hand rule. So this is supposed to be this. The first finger showing the direction of the magnetic field, second finger in the direction of the current, and then your thumb shows the thrust or the force. But just don't judge me. Okay. Right, now question 5 was tricky. A bunch of people struggled with it. So some people asked me about it, and some people I could just tell from your pictures you found it tricky or you couldn't quite follow it. So let's go through it. So use Fleming's left-hand rule to complete the following exercises. So these diagrams here, we had to draw arrows on to show the directions of the forces on the current carrying wires. Now, this wee bit here, I know this is quite blurry, but this wee bit here tells us what to do, or what's going on actually. So if we have the circle with the wee X in it, that means the current is coming out of, so perpendicular to the page, not coming out of, and going into the page. So this one here is like you're looking down the end of a wire, and it's like, so suppose if I show you, that's going to be too, okay, so like the pen is the wire, like you're looking down, and the current is going down into the page. This one, the circle with the wee dot in it, means current is perpendicular to and out of the page. So here again, there's my pen, so that's the wire, but this time the current is coming up out of the page. So I'll show you how I figured these out. I'm going to start with this one. Now this one's really awkward to get your hand into the right shape, but first finger in the direction of the magnetic field, so that's down the way. Second finger in the direction of the current, so let me remind myself. The one with the X means the current's going into the page. So, second finger into the page. First finger in the direction of the current, so north to south. And then your thumb's pointing to the left. I really didn't show that very well, I promise. It works. Try it. This one is a bit easier to show you. So, get your Fleming's left-hand rule. First finger in the direction of the magnetic field. Second finger in the direction of the current. This one coming out of the page. So field, current coming out, thumbs pointing to the right. So this one's going to shift off to the right. Okay, part B. This one here was a wee bit awkward and people generally didn't ask me about it. I was quite surprised. So here in both of these, they've given us 2 pieces of information and we have to figure out the third. Okay, so in this one, they'd give us the magnetic field going from north to south because they'd labelled north and south on this diagram. And they told us that the force was off to the right. So we had to figure out what direction the current was coming in. So again, Fleming's left-hand rule. First finger in the direction of the magnetic field, so north to south. Your thumb in the direction of the force. So see how if I do that with my hand, with my first finger going north to south, thumb in the direction of this force pointing to the left. My second finger is pointing up out of the page. So the way that they had drawn that earlier was the circle with the wee dot, but I labelled it like that as well. Same here then, this time they had given us the direction of the current. So this one's going into the page and the force going off to the right this time. And the missing piece of information here then was the direction of the magnetic field. So Fleming's left hand. Let me go current first of all into the page. So I've got my middle finger going down into the page, thumb in the direction of the force, that's over that way. So because my first finger is pointing up the way, that's the direction of my magnetic field. So this must be north and this must be south. And then these ones here, question 6 on 225, you had to say which ones of these were AC and which ones were DC. So if it's direct current, your current will not cross that x-axis because it's always going in the one direction. So this one is DC. This one here, although it's changed in size, it's always the same direction because it's always like above the x-axis. So it's DC. This one here, again, change in size, but not crossing that x-axis, so it's always in the same direction, so it's DC as well. These two are both AC because they are changing from one side of the x-axis to the other. So these two are constantly changing direction. So they're both alternating current AC. DC, remember, stands for direct current. So we're going to look at electromagnetic induction today, okay? This is basically the opposite of what we have been talking about there with the electric motor. So if you remember, with the electric motor, if you have current flowing in a wire and that's in the presence of a magnetic field, then the wire is going to move. This time what we're looking at is if we have a wire and we move it within a magnetic field, a current will be produced. Okay, that's basically it. So it is the opposite of the electric motor. Okay, so if you connect a straight piece of wire to a sensitive galvanometer, that's just like an ammeter that reads really small values, and move the wire across a strong magnetic field, a current is produced. So this type of current is called an induced current. Okay, so there's a few terms that we're going to have to get used to here. But yeah, if we just move a wire within a magnetic field, if the magnetic field is strong enough and you have an ammeter that reads a small enough current, you will find that you get a wee current being produced. Now, there's a little bit more to it than that, but that's the crux of it. So down at the bottom here, so Faraday found that if a wire is moved to cut through the lines of flux, remember lines of flux is just another word for the magnetic field lines, a current will be induced in the wire. So see the way this here is perpendicular to the lines of flux or the magnetic field lines? That's what we mean by cutting through. If this was parallel to the magnetic field lines, and you'll remember this from the motor as well, then nothing happens, like the current isn't induced. So you're going to get maximum current whenever these two things are perpendicular to each other. And remember, perpendicular is what we're doing whenever we do that Fleming's left hand rule. We're making sure all our fingers and thumbs are perpendicular to each other, and it's because of this. Right, I think it says that down the bottom here. So this is called electromagnetic induction. So we're getting a current induced, an electric current induced whenever we're in a magnetic field, so electromagnetic induction. So the electrons in the wire have been given a push as the wire moves across the magnetic field. If the wire moves parallel to or along the magnetic field lines, there's no current. It has to cut across perpendicular to get the maximum. So over on to 227. Now before I even showed you this, or before you even read it, you probably could have guessed what's going to make the current stronger. So if you have a stronger magnet, you're going to have a stronger magnetic field, you're going to get more current being produced. If the wire gets moved through that faster, then you're going to get more current produced. And if you, instead of just using one wee wire, if you have a coil of wire and you increase the number of turns on that, you're going to get more current induced. Okay, so that is one way that current can be induced in a wire, just by moving a wire through the magnetic field. So that was moving the wire and the magnetic field staying constant. The other way is shown here. So in this version, we have a wire that is staying stationary. So it's just a coil of wire, but this time we're moving the magnetic field. So really it doesn't matter which one is moving, as long as the magnetic field and the wire are moving relative to each other. So one of them be moving. Now, this here is going to be the main focus of what we're looking at today. So if a coil of wire is connected to a center 0 ammeter, that is important. So see the way here, at this point here there's no current, so this is the 0 mark on our ammeter, and then we would have positive current for current going in one direction, and then a negative current for current going in the other direction. Right, so center 0 ammeter, and a magnet is moved into the coil as shown here. The following occurs. So this first one, when the magnet is moving in, so in this one here the magnet is moving in and it's going inside that wee coil of wire, you can see here we've got a wee current. I'm going to say to the right is positive, so we've got a wee positive current here. Now that current is only there whenever the magnet is moving, because do you remember back here on 226 we only got the current being induced whenever the wire was moving relative to the magnetic field. So it's the same here. Whenever the magnet is moving, you've got a current. As soon as that magnet is stationary inside that coil of wire, no current is going to be being induced. Now, on this third wee diagram here, you can see the person's moving the magnet out of the coil. So because the magnet's moving in the opposite direction, our current is induced in the opposite direction. And you can see that there with the wee galvanometer with the arrows now pointing over to the left. So this would be a negative current. Now see this? The whole thing with moving one way gives you a current in one direction. Stationary, no current. Moving the other way gives you current in the other direction. That is key, really, really key to one of the last things that we're going to do here this year, the transformers topic. Well, it's within this topic, but the transformers section. Understanding this, and vitally, whenever there's no movement, there's no current being produced, and the direction affecting, the direction of the movement of the field affecting the direction of the current, that is key to that. So do keep pausing me and making sure that you're following what's going on, because I might be going too quickly here and then I'll all be lost. So this text down at the bottom here, each one of these correlates to each one of these diagrams. So this here diagram, whenever the magnet's moving in, when the magnet is moved in, the current flows one way, i.e. the ammeter deflects in one direction, then goes back to 0 when the field lines are no longer being cut. So once it's held still, it's going to go back to 0. So this diagram correlates with this wee paragraph here. When the magnet is held still, no current flows, so the ammeter stays at 0. Then this one correlates to this. So when the magnet is pulled out, the current flows the other way, i.e. the ammeter deflects in the other direction. Then it goes back to 0 again when no field lines are being cut. So do make sure you note the direction of those arrows on the ammeter there. Now, this is one of those things that I always kind of forget, but every year whenever I read back over it again, I'm like, oh yeah, it's fine, so bear with me. I was just saying there that when the magnet moves in one direction, the current goes in one direction, and whenever it goes in the other direction, the current goes in the other direction. So we can use Lenz's law to figure out those directions, and it's like a wee clever wee thing. I love all these wee rules with the hands and things. I think they're so clever. Anyway, the current always flows in the direction that will set up a magnetic field to oppose the motion causing it. Now, again, you're probably thinking, what is she on about? This here bit explains it really well. So we've got this hand and it's moving the magnet into the coil that way. So we've got our wee coil of wire, we've got our magnet moving in. Now to add confusion here, I don't like this wee diagram because you can't tell which bit of the coil is at the front and which is the back. So we'll get there. So the magnet is moving with its north pole towards the coil. So you can just about make out that wee north there. Now, do you remember this? The current always flows in the direction that will set up a magnetic field to oppose the motion causing it. This here, this hand, is pushing this magnet in. So if we're thinking what's going to oppose that, then it must mean that this side of the coil is a north pole, because then they're repelling each other and it's opposing. So that's just what it says here. So this means the left hand side of the coil must be a north pole, always opposing the motion, trying to repel. So work must be done to push the magnet in, and it's that pushing force that generates the electrical energy, because remember, energy cannot be created or destroyed. When you change from one form to another, we can't magic up this electrical energy. It has to come from somewhere, and that's where it comes from, because there has to be energy put in to oppose this motion. So we're going to go back to use the right hand grip rule. Now I can guarantee that page number's wrong. Hold on, I'll look up what it actually is. So it's page 208 in your notes. So do you remember this one where you put your fingers in the direction of the current and your thumb points to north? Well, now we know that this end of this coil has to be a north pole. So we're going to put our thumb in the direction of north and our fingers will show us the direction of the current. So what's going on here is I'm going to draw, let me see, because you can't tell which ones of these is at the front and which one's at the back. There's the back. So I'm going to do a pink line up the front of this coil, if that makes sense to you. So up the front of the coil, and the current is going up at the front bit there. Okay, now that I've drawn it in, I can visualize it that way with those bits of the coil at the front. But if I use my right hand grip rule here, I'm putting my thumb towards north and my fingers are gripping around this coil in the direction that the current is going. So it's going up at the front and then it's going down at the back. Okay, so then you can use that to figure out what direction the current's going. Now, down at the bottom, we just have the same but opposite. So again, that page number's wrong, 208. So remember, the current always flows to produce a magnetic field to oppose the motion. So this time, this person's moving this magnet away. Now, opposing that means it's going to want to attract. If you're moving it away, it's going to want to attract. So that must mean that this end is a south pole and this end is a north pole. So if we use our right hand grip rule for that, then thumb towards north, our current must be going up the back of this and then down at the front. And again, that's what that diagram's showing. So again, I will mark on using pink pen the front of this coil. Okay, so down at the front. And we can just use that right hand grip rule. Thumb points to north, your finger is going to show the direction of the current. So that's what this is saying here. The magnet is moving with its north pole away from the coil. This means the left hand side of the coil must be a south pole, always opposing the motion, trying to attract, so work must be done to pull the magnet away, and that's what generates the electrical energy. Okay, now that is like high level stuff. It will take you a wee bit of time to get your head around it, so do take the time. This video is not going to take up the whole lesson, so make sure you are taking your time to slow down, do everything with your hands, and yeah, trying to make sure you grasp this as best as you can, and remember to keep asking questions. Now, on page 229, let's have a wee look at that. Electromagnetic induction can happen when either a magnet moves into or out of a coil of wire, or we move a coil of wire within a magnetic field. Remember, as long as one of those two things is moving, it means the two things are moving relative to each other. And remember, electromagnetic induction just means that you are producing a current in a wire whenever you're in the presence of a magnetic field. So it's the relative movement between the magnet and the coil that induces electric current. Doesn't matter which one is moving. When a current is produced by electromagnetic induction, energy is always needed to create the electrical energy. On page, again, wrong, sorry, on page 228, that last page we were just on, the energy came from the person moving the magnet. So electromagnetic induction is a way of converting mechanical energy, that's the way we tend to just say moving energy, into electrical energy. And this is the principle behind transformers and electricity generation in power stations. Ever so slight sidetrack here. Do you remember last year whenever we were learning about all the different productions of energy? I worded that weird. But everything came down to, if you move a turbine, turbine turns a generator, generator generates electricity. This is the basis of that. The something moving in the presence of a magnetic field is going to generate current. So next lesson, we're going to look at, I know we have to fill this in, don't worry, but next lesson we're going to look at the AC generator. So how this principle of electromagnetic induction can be used to produce electricity. For now, if we just fill in this is the type of thing that they would ask. So how can the size of the induced current be increased? We can move the magnet or the wire, whichever one's moving faster. We can use a stronger magnet, or we can use a coil with a greater number of turns. Okay, get that written in for me. Do spend a bit of time trying to make sure you understand that, because it is the key to the rest of the stuff that we're doing here. Okay, that's me. See you next time. Bye.